Okay, guys, discrete optimization, part 6. Okay, so once again, what we're going to do is using the tools that we have built so far and trying to build better models. Okay, so we know some of the techniques that we have, and what I want to show you today is how to use redundant constraints to speed up models tremendously. Okay, now what is a redundant constraints? Okay, so essentially, these are constraints that don't add anything to your model from a semantic standpoint. Okay, the model will have the same exact number of solutions. Okay, but they are computationally significant because they will prune the search placement more. So in a sense, so you put them in the model, they don't remove solution, but they decrease the search space. And so once you find these constraints, they are very, very useful from a computational standpoint. Of course, the question is, how do I find them? And in general, they capture really interesting properties of the solution. You look at your problem and you say, oh, but for something to be a feasible solution, it has to satisfy this. And typically that's a constraint. You take that constraint, you put it in the model, and in constraint programming, the more of these you put inside the model, the faster your computation is going to be. Okay? So it's a critical aspect of constraint programming. Most of the time, you try to capture as tightly as possible this set of solutions by expressing the constraints as best as you can. Okay, so I'm going to use a couple of simple examples, to illustrate this. Remember the magic series? Okay, so we wanted to find numbers from S0 to Sn, such that Si represent the number of occurrences of I inside the series. Okay, so I'd asked you last time, we could actually find this series. This is a beautiful one. Okay, so we see, there are two instances of 0. There is one instance of 1 itself. There is two instances of 2, itself, and the first one. Okay, and there are obviously zero occurrences of 3, 0 occurrences of 4. Okay, now, so this is the model that we saw last time. And what I was, one of the things that I'm asking you is, can you find the properties that the solutions have to satisfy? Now, when you look at the array of decision variables series, can you find a constraints that is actually helping? Will help, in addition to these constraints that we have stated. So we have this constraint which is stated. It actually captures exactly what are the solutions. But can I find another constraint which is always true for every solution, but which will give the solver much more information? And that basically means the solver will be able to exploit it to remove values from the domain of the variables, because that's the end of, that's the rule of the game essentially. Okay? So typically, the way you do this is that you exaggerate, right? So look at this thing, okay? So this is my magic series, and I'm asking you, can I put 17 there, right? I'm exaggerating, right? So nobody would do that, okay? I put 2,000 there. It makes no sense. Why? Because what is 17 denoting there? 17 would denote the number of occurrences of 4 in the series. No, that series is, 5 of length 5. If I put 17, obviously I won't be able to put 17 occurrences of 4. Okay? So in a sense, what do I know? Can I deduce something which is interesting on the sum of the numbers on this series? Yes, they are all occurrences. How many occurrences can I have? Well, the length of the series. Okay, so I can have this beautiful, essentially, constraint which says that the sum of all the elements in the series have to be equal to the length of the series, which is n. Okay, so this constraint has to be true. It must be true. There is no other way. Okay, so the number of occurrences is n. Okay, and since these decision variables are denoting the number of occurrences, okay, the sum of them cannot be more than n. So this is a constraint which is redundant from a semantic standpoint. It will never remove any solution. Every solution will satisfy those constraints, but it will be able to prune the search space better. Okay, so can I do better than this? Okay, can I find actually something which is stronger than that? Look at this thing. Okay, so what am I writing? Assume that series 2 is equal to 3. What does that really mean? That basically means that the value here, okay, I'm going to put a 3 over there. Okay, what does it mean? It means essentially that there are 3 2 in this array. Okay, so far so good. That's what we know. But saying that there are 3 2's in this array means what? How many occurrences does that count for? Well, essentially, these guys, there are 3 2's. Okay, so two occurrences, and we have that 3 times. So that means that there are 6 occurrences. Okay, so essentially what we know is that there is another way for actually counting the number of occurrences. Instead of summing every element in the series, what you could do is look at every element in the series, okay, and then multiply it by I. So you look at every element of the series, let's say element I, and you multiply it by I, because what I had before was what? Series 2 was 3, so I multiplied by 2, that makes 6 occurrences, okay? So it's another way of computing the same information, okay? So I have another redundant constraint, which is basically the summation of I, times series I has to be equal to the number of occurrences, which is n, okay? So that's another constraint. Which one of the two that I've shown you before is stronger? Okay? I will tell you a little bit which one is stronger. Okay? But it doesn't matter, right? We could put the first one, we could put the second one inside the solver, and let the solver propagate these two constraints at the same time. Okay? But let me show you the kind of deduction that you can do. Okay? So this is essentially only taking the second one here, okay? Which is stronger in almost all the cases. There is one case where it's not, but almost all the cases it is stronger. So you see essentially the constraints that I've shown you before, but then you see this redundant constraint which is over there, okay? And what is interesting is what? Okay, so you see a 5 there, okay? And you see, this guy is multiplied by 4, right? What does that mean? Okay? That means that the maximum value that series 4 can take is what? Well, it's 1, right? And the same thing for series 3. And for series 2, the maximum value is going to be 2, okay? Otherwise, I would exceed this 5, okay? And for 1 is going to be, 5, okay? So immediately, I can deduce very strong information here on the value of these variables, okay? And I can use that for pruning the search space. Very quickly, many of these reified constraints can disappear, okay? Because I know that they can't be true. Okay, so essentially here, I have removed about a third of this constraint. Okay, then assume that I make a very simple choice. I said that series 0 is equal to 2. Okay, so that basically means that I put a 2 over there, right? So you see the 2 over there. Okay, it also means that I have a 2, right? And therefore, the value that you see here for series 2 here, I have already a 1 over there. Okay. And then you look at the constraints, the redundant constraints that I have added. Okay, so what do you see there? I know that series 2 is greater than 0 now. Okay, so, and therefore, when you look at these constraints, essentially the 5 has become a 3. Okay, and therefore, I can immediately deduce, okay, that series 4 here has to be equal to 0 because it multiplied by a coefficient 4 and can be at most 3. And that the other one, the 3 times series 3, can be at most, 1. Okay, so once again, I can use that information and I can start propagating that information and my search space become much smaller. Okay, so if you use the simple model that I've just shown you, you can solve magic series up to really, really large numbers. And if you do that, if you actually implement this beautiful model, you will see a very nice patterns in the way these solutions are actually being basically constructed and the similarities that they have with each other. Okay, so the first role of the redundant constraints is to express properties of the solution. And because it looks at the problem, the redundant constraints is looking at the problem from a different angle, it's going to boost the propagation. Okay, so in a sense, what you are adding is these new constraints inside the overall model. You had all these constraints which were already there. They were pruning the search space independently. You add a new one, and that one will also reduce these domains, and therefore will have an impact on the other one. That's the first role of redundant constraint. Okay? So I'm going to show you another role. This is the second role, which is to provide a global view, a more global view. Okay? So and what I'm going to show you is that you can actually combine existing constraints, and that combination will improve the communication between the various variables. Okay? So I'm going to illustrate that with a market split problem. Okay? And essentially, once again, so you can think of it as a multi-knapsack, except that the constraints, instead of being small or equal, are going to be equal. Okay? So what you have is a set of constraints, a set of you will have a set of constraints, indexed by C, a set of variable indexed by V. Okay? For every value in C and V, you will have essentially a weight. Okay? You can think of a knapsack and the multiple dimensions. That's the WCV. Okay? And then you have a right-hand side. You can think of it as a capacity. Okay? And then the decision variables are going to be this value x, and there is one variable for every element of V. Okay? And then the constraints are essentially kind of knapsack constraints, except that it's an equality and not small or equal. But what you do is you basically multiply the weight and the variable, okay, for every one of these constraints, and you want that to be equal to the right-hand side. Okay? Now, these constraints are actually pretty weak from a propagation standpoint. They don't communicate through each other, only through the domain. And in this particular case, you have these linear constraints that are basically doing their work independently, and they communicate very little. Okay? So one of the things you can do, okay, is use the concept of surrogate constraints. So you take all these constraints and you add them, every one with a different coefficient. Okay? So I'm basically using here, alpha to the power of c. Okay? And by essentially multiplying the first constraint by alpha, the second constraint by alpha squared, the third constraint by alpha cubed, and so on, okay, I can combine all these constraints. I also multiply the right-hand side here, okay? And therefore, this is essentially a linear combination of all the existing constraints, and it's valid, obviously. It's not going to remove any solution, and I can add it to the solver. So what I did was essentially taking constraints that are completely independent, merging them together, and now they are working on the same set of variables, and they're going to prune the search space more, okay? So surrogate constraints, they are used in constraint programming. They are used in mathematical programming as well. We may talk about that later on, okay? But essentially what I'm doing is simple combination, in this particular case, linear combination of existing constraints, okay? So in a sense, a surrogate constraint is just a new constraint that I add, like the properties of the solution that I've shown you before, except that this time, I'm not expressing the properties of the solution per se as something that I discover. I'm simply taking existing constraints, combining them, and getting these new constraints that I put inside a constraint solver. Once again, by definition, if I add new constraint, the only thing that can happen is that I prune more. In the worst case, I prune the same, okay? And so in some application, it can make a big difference. Thank you.